Thank you. Thank you very much for the introduction. And I'm Ahmad Reza. I'm a postdoc at KTH, Sweden. And first of all, I want to thank the organizer for giving me this opportunity and thank you for being here, the first session. And today's talk, I will be explaining about the hybrid networks that I'm working on. But before that, I'm going to explain briefly two of the works that I did during my PhD because the works are the foundation of today's talk. So the group that I'm coming from in Sweden, they're interested in nanofiber networks. So they work with biopolymers, different biopolymers, to make advanced material and make the best use of these structures. So these structures they have like interesting properties that scientists try to make those synthetically in the labs to be implemented in different applications. But we should consider that these are like complex systems. For example, in this picture that it's taken from this paper below, it shows a cell that it tries to diffuse in an extracellular matrix. So these matrices, they provide, first of all, a structural integrity for the system. So it provides an environment for different phenomena that happens in those structures. And they have open networks, so easily, like different materials, depending on the size and the charge that they have, they can diffuse or stick to the system. So the important facts that we should consider is that the important one is that they have thermal motion, so they have they are dynamic systems. And depending on the condition of the system, they show different flexibility behaviors. And of course, when they are crowded and they interact with each other, they show collective behavior. And the most important one that I'm most interested in is that they are charged, usually. So the first thing that we knew is that the flexibility matters. So when the rotation theory was developed, it was originally developed for flexible polymers. But thanks to Doi and Edwards, it was like extended for rigid polymers and rigid with the polymers with high stiffness. But since most of the biopolymers they show like semi-flexible behavior, these are the time that I started there was no there were a couple of like a theory, but they were contracting each other. So that was the point that we tried to do the simulations for to make a system in a crowded network with semi-flexible polymers. So as you can see here, I use like Espresso MD packages, which is based in Stuttgart University, and the forces that the force field that we have is like based on the simulations. We can have like Lennard-Jones potential. And for electrostatic interactions, we use like P3M algorithm. And of course, the polymers are made with beta spring models. And in the cases that we want to consider the hydrodynamic effects, we couple the simulations with Lattice-Boltzmann method, which is a non-trivial task, I would say. So the challenges that we had was due to the crowd environment. Since we wanted to get the rotation behavior, we were forced to go high concentrations. So we had a cubic simulation box, 3D like periodic, and we choose the box length larger than the polymers to be able to get the correct physics. And since we have like large fibers, large polymers, and flexible ones, the warming up of the system, it's a time-consuming procedure. Even the production part is a time-consuming procedure. And of course, since we have like a small box compared to the number of polymers, the introduction of the polymers is even like it was a little bit challenging. So the first work that we did was to have a crowded network of semi-flexible polymers. And we were able to propose a scaling behavior for the rotational diffusion of the biopolymers, semi-flexible polymers. And also compare it with Doi Edwards and Odic theory. And here we see that, and one of the main points of this paper was to analyze the tubes that they are in the system. So what you see here is the empty spaces in the polymers that they are changing in the size, they rotate, and they are not stable. And we have been able to estimate the size of these polymers. So, but in the next step of the project, we were interested in the diffusion in these systems. When we add let's say, charged nanoparticle, which oppositely charge, how they can diffuse in the system. And why this is important? Because in this paper that you can see here is that one of the most common methods for designing nanoparticle drugs are charge regulations. And when they implement them, they have shown that only 0.7% of the particles can reach the target because of the charge. Even they are smaller than the mesh size of the system, that they can easily diffuse, but because of the charge, they stick to the surface or to the, let's say, extracellular matrices. So what we did here is to consider all these effects, the charge ratio between the nanoparticles and the biopolymers, and the concentration and the size of nanoparticle as well, and to analyze and to see what's the physics behind the sticking, sliding, and the bouncing behavior. So what we were interested in was the fate of nanoparticles, what happens to the nanoparticles, because they reported that some of them they stick, some of them they slide on the fibers, but some of them are directed to different directions, like that they cannot reach the target. So we were able to analyze the dynamics and propose like the three different dynamics that they can, like all three of them, they can be useful compared to the application that they can be used. And in this figure, we were able to connect the size of nanoparticle, concentration of the polymers, and the charge the charge ratio between the nanoparticle and biopolymers to predict the dynamics of the nanoparticle into the system. So somehow with the size, charge, and charge of biopolymers, we can predict that this nanoparticle will diffuse into the system or stick to the fibers. But today's talk was actually at the last year of my PhD. I was visiting a lab at EMPA, Switzerland, and they work also on the same systems, biopolymer systems, but they try to mix different oppositely charged polymers to see to analyze their rheological behavior and like the structures that they can create. And as you know, these hybrid networks has like so many applications that people are like working on at the moment. And as you know that so when we mix two oppositely charged biopolymers, we have like a dense phase, which is coacervate, and a supernatant, which is the dilute phase. So they already had like a system that they published it already. They mix like amyloid fibrils with cellulose nanocrystals and cellulose nanofibers, and they do analysis of the self-assembly and the structures that they can create. So what I did was to use this paper, and they asked me to if I'm able to simulate these systems. So what I did was to use this paper, which is Professor Rubinstein, and I used the electrostatic blob like model to create these systems. And these are the most important parameters that we have in the system, and we define the blobs. If I want to define it, is the segment size where electrostatic energy is comparable with thermal energy. So in each blobs, we have monomers with charge fractions that when they interact with each other, the energy is comparable with the thermal energy that we have. And of course, when they create the structures, there are like some correlation lengths that you can get from the system. The correlation lengths, I would say, it's the mean or average distance of the polyelectrolytes from each other. So at the first step of this work, I wanted to validate the system. So after creating a polyelectrolyte network and the counter ions, I measured the correlation length of the system, and I compared with the proposed model by Rubinstein that we were able to validate it in a good manner, I would say. But when it comes to calculations, when we want to mix, for example, amyloid fibers, that they are like semi-flexible, positively charged, with CNC that they are short and rigid and high charge. So when we do the calculation for the blobs and we set the flexibility and the rigidity, we come to a point that so what happens when flexibility changes? So one of them is semi-flexible, the other one is rigid, and also they are charge asymmetric. So they are not like, they don't have the same charge fractions. So before going to get the rheological behavior from these systems, we did some tests to see how these systems behavior and what is the exact effect of flexibility and charge asymmetry in these systems. So we have, in the systems, we have polyelectrolytes with their counter ions. And in some cases that we needed, we have added salts, ions into the system. We introduce them. And simulation continues to, that the assembly and coacervation happens in the systems. And we define the rich polymer regions. So whenever I say coacervate here, I mean the rich polymer regions that we have in the simulation box. And for example, here you can see one of the examples. For example, this part is the rich polymer region that we define it as coacervate. So the first, to isolate the effect of flexibility, I made a system with identical oppositely charged polyelectrolytes, and without losing generality, I defined the polycation to be fully flexible and change the flexibility of polyanion to see the effect of flexibility. And as you can see here, the more rigid polymers that we have in the system, I would say that it's not favorable for creation of coacervations. And the critical salt and the volume fraction of coacervation decreases with more rigid polymers. And of course, it has a reason that flexibility allows more like connected points of the polyelectrolytes, and they create more dense, I would say, coarse-grained. And of course, when you have such system, the salt tolerance increases into the system. But charge asymmetry effect, I would say, is the most important part. So we have like two identical, or two type of identical polyelectrolytes with the same flexibility, but we change the charge fraction. Compare how the charge fraction affect the conservation net charge. And as you can see here, when we define R as the charge fraction of polycation to polyanion, and as you can see here, in a symmetric case, which R is equal to 1, we have a net charge of 0 for the conservation. So it means that the system is balanced in case of charge. But when we change the R, we increase it, we see that the conservate, the region, has a net charge. And this net charge, I would say, disturb the system because it's an imbalance. And this net charge needs to be neutralized with the help of counterions or salt. So in these cases, when we have a charge coarse-grained, we have like fewer counterion release in the systems because the counterions will be directed to the coarse-grained direction. Now, of course, these systems need some more time numerically to reach the equilibrium. So one of the things that I was interested in was the salt partitioning part. When we add salt into these systems with charge asymmetry, what happens to the salt partitioning? Because this is I would say, the point that different theories that we have different predictions. So actually, I was confused. I even talked to Mehdi about it. That when I wanted to calculate this, like a salt partitioning, I was confused that should I consider counterions, like the counterions related to polyelectrolytes, into account or not, or just go with the salt ions. But what you see here is the total positive counterions, including the polyelectrolyte counterions plus salt. And so it's all the charge into the system. And as you can see here, in a case of a symmetric case, again, with R equal to 1, you can see that the salt partitioning coefficient is almost equal to 1. It means that the salt is divided equally between the coarse-grained phase and the supernatant one. But of course, with the change of the charge, we have this behavior that shows that, for example, for R smaller than 1, it's like salt excluded from the coarse-grained, but for higher R larger than 1 is salt enriched. So we can say that charge asymmetry controls the coarse-grained takes up or dilute the salt into the environment. One of the things that I would say I was interested is that in the binodal graphs that we have, what happens to the tie lines, at the slope of the tie lines. And for like 3 different, in the same polymer concentration with 3 different salt concentration, I checked how this slope can change with the salt, with the effect of charge asymmetry. And as you can see here, the circle ones are for like a symmetric case when we have R equal to 1 or the polyelectrolytes have the same charge distribution. But for the square and the triangle, we see that this slope increases, or even for higher like charge asymmetry cases, the slope flip to positive. And these looks, I would say, like familiar compared to the theories that we can see. For example, the positive slope reminds us the original like Theo theory. And yeah, but when we have like a symmetry case, it's like in line with most of the like or experiments that they report a negative slope of the line. So, and one of the things, it's really difficult numerically to get to, okay, thank you. It's really difficult to get numerically these graphs. So that's why, but if you just, if you connect, for example, the spherical cases, you can somehow see the model lines. So, and here I go like quickly, I go back to the case that I had, like amyloid and CNCs, and they had like some visualization from AFM results, and that we could capture the kind of like structures that we make and the bundle sizes that they were made it, they had it in the experiments, and we were able to see it in the simulations. And one of the things that was the main goal of the project was to do the microreological. So in the cluster weight phase, we added a bead to diffuse into the system and get the rheological behavior. And we were able to like compare it with some of the reported results in the literature. They like connect the G0 or plateau, like the plateau region of the rheological behavior with the concentration of the biopolymer. And this is the conclusion of the, I would say, the hybrid section of my presentation, that flexibility enhances conservations. Of course, it was reported like the first one in the literature before, but what was important for me to see how we can like quantify this. And of course, the other one, the charge asymmetry, that it affects like almost everything, solid partitioning, and the take-up procedure of the conservation. And we can see that we can say that the phase behavior is kind of tunable, that if we want to control. And the last one was one of the things that I was really happy about, was to see the slopes of the lines and compare it with the theory. Thank you so much.